I'm Mike Saunders, principal consultant at Red Siege. And so what I want to talk to you about today is some shellcode obfuscation techniques that I came up with. I do want to preface with, I wrote these tools. I believe in the case of Jargon, I am the first person to publish this technique. I'm not the only person to have come up with this technique. I've talked to other people who have also written that tool, but they didn't publish it. I've seen it proposed elsewhere, but I was the first person to actually write some tooling as far as I'm aware of for this. However, there was a talk at DEF CON where someone used shellcode as emojis, or emojis as shellcode, but that was for the RISC architecture, but it came out, I'd already written this tool, but they got to give that talk first because I didn't submit. So here we go, Jargon. If you want the slides, you can grab the slides. They're at redsiege.com/jargon-toolshed, and I will show this link again at the end of it, and it will end up going in the Discord as well, so you'll be able to get a chance to see these slides. Feel free to take pictures if you want, but they will be available. So, I'm the principal consultant at Red Siege. I've been in IT a long time, been in security for a bit, and that just means that I'm old. So, mainly what I like to do these days is touch grass and get outside, and I love photography and music, and wow, that was a really weird way to pronounce that, music, and hiking, and so that's what I like to do. So if you like to see pictures, follow my social medias, that's where you'll find them. But enough about me. Let's talk about entropy. I'm talking about entropy in the kind of information theory kind of space. We're not talking about the heat death of the universe. However, I understand that entropy is kind of all related, and I know just enough to tell you about this. Please do not ask any deep entropy questions. So entropy is a measure of the amount of randomness in something. And again, I'm not a mathematician. But we're going to be talking about entropy as it relates to information theory, and we're also going to dip into this thing called Kolmogorov complexity and how that relates to compression and entropy. So roughly, entropy is a measure of the amount of randomness in something. So if something is really high in entropy, it is very random. If something is very low in entropy, it is very not random. And Kolmogorov complexity comes in because it tells us if something is very random, it is not compressible. So if you've ever tried to zip something and it doesn't compress very much, it's very high in entropy. You cannot compress high entropy data. However, if something is very low in entropy, it's very compressible. So I did a test. I read in a bunch of bytes from dev-urandom, which hopefully is a very random information source. And I tried to compress it, and gzip is a good proxy. This isn't the best way of measuring entropy, but it's a good proxy for it. And you can see that I was able to compress it by 0.0%. So, if I could not compress it at all, is the entropy high or low? High. Very good. That is correct. Because I could not compress it, Kolmogorov complexity tells us that it is high in entropy. It's random. So we have a problem. We need to evade detection with our shellcode. We do a lot of things, but we don't want our shellcode to get detected. So we have to obfuscate it. One of the ways we do that is by encrypting it. However, when we encrypt it, we increase entropy. And some EDRs measure entropy and use that as a proxy to determine if something is trustworthy. And if it's high in entropy, it's a signal that you might be trying to hide something. And so therefore, maybe give it more scrutiny or don't allow it to run. Now, languages, and I'm talking about, English, Spanish, German, whatever, they are not random. We know this. We can test it. So let's do the gzip test. And we'll gzip a English dictionary called dictionary.txt. I was able to compress it by 64.7%. So I compressed it a lot, so we know that it's not that random. And then I took a German dictionary and I compressed it, and I was able to compress it by 75.9%. So that tells me not only is German more terrifying than English, it is also less random than English. So There are two really interesting articles here. They're kind of a side detour that are talking about like actually encrypting shellcode in written text. So you open up a shellcode loader and there's Shakespeare in there. It's actually shellcode. And that's not quite what I'm doing here, but it's terribly interesting, written by some incredibly smart people, and I encourage you to go check that out. So the whole reason this came about is I was on a test and there was Crowdstrike. And I take this loader and it has AES encrypted shellcode, and I drop it on the box and I try to run it. And nothing happens. Like no command window pops up. I don't get any errors, nothing. So I open up the command line and I try to run the program manually. And I just get back a C prompt. Again, no errors, nothing. So like any really well-versed, skilled programmer, I inserted a bunch of printf statements in my code to tell out where I was at. And then I uploaded that new version to the system. And I ran it. And the first thing that program should have done was printed out, hey, I'm starting to execute. And I never even got that. So that tells me the program isn't failing, it is not running at all. So something on that system is making a decision that this program is untrustworthy for execution. Well, it must be Crowdstrike. They've got this machine learning AV component, and it looks at unknown executables and makes decisions about whether or not they might be trustworthy. Well, I've got this thing that's very high in entropy, and it's not letting me run. So the answer must be lowering the entropy. Maybe I can run. So I did. This is my absolutely ghetto fabulous hack for getting it to work. I created a variable in my code called anti-entropy. And there are 7,740 words in this array. There's no magic to that number. That's how many that happen to be in dictionary.txt. And I compiled them in. Now I disabled compiler optimization because compiler optimization will be like, hey, this code does absolutely nothing. Let me help you out and get rid of it. So I had to disable compiler optimization. And I compile my payload with this in here. It does nothing. I never do anything with this array. I just compile it in. So now we can see the first one, AES.exe, that is my loader with AES encrypted shellcode. It's not that big, like it's 362K, and I tried to compress it, and I can only compress it by 18.4%. AES plus words is the same program with this array compiled in. Now it's much bigger, it's 15 megs, and some of you old school people might be like, oh my God, that shellcode loader is so huge. Well, it is, but everyone's got a fast internet connection. We don't really care about having the smallest possible loader ever anymore. So my 15 meg payload, I'm able to compress it by 97.8%. It's highly compressible, so is it very random? No, it is not. I've lowered the entropy by simply compiling in a bunch of words and enter in jargon. Like, there's got to be a more elegant way to do this. I've got a shellcode loader that I've gotten around now by compiling in words, but it still contains shellcode. What if I could have a shellcode loader that did not contain any shellcode, but still executed shellcode? What does that look like? How would I do that? I thought about this, and the term jargon, you can see the definition here, kind of, special words or expressions that are used by a particular profession that are difficult for others to understand. So I want my loader to be difficult for EDR to understand. And that's how I came up with the term jargon, thanks to one of our employees. So I want to take this further. I want to take my shellcode and I want to encode it as English words. Note that English words, because that's what I was using, but you could use any printable character set for doing this. So I've got English words. If I can do this, yeah, emojis. You could do it with emojis. So if you take English words, you avoid having raw shellcode in your loader, and we know that English is not random. It lowers our entropy. So the basic of how it works is we can store shellcode We normally see it written as like, 0x00, 0x01, so on and so forth. But we could also store it as an int. We could just store it as 0, because 0x00 is 0. So with that idea in mind, if I have an array of words, and if I have an array of like 256 unique words, I need 256 unique words because why? 256 bits in a byte type thing, that's not quite the right math, but you're on the right track. There's 256 unique characters in hex, 0x00 through 0xFF. So if I have an array of 256 unique words, the index of each word in the array represents a specific number. So the first entry in that array represents 0x00 or 0. The last entry in the array represents 0xFF or 255. So now I've got 256 unique words that each represents a byte of shellcode. And the source could be anything. I used English words, but if you really wanted to screw with an analyst's head, get all the unique strings from, say, kernel32.dll and use those. It works. And now you've got this loader, you're looking at this program that's just full of API calls. Like, what is going on here? There's no shellcode, it's just API calls. So with this translation table of 256 unique words, we can start encrypting our shellcode. So we look up our byte of shellcode, and we see that the result is 0x00. So the first word in my array is attending. So I'm going to create a new array called called like translated shellcode, and I'm going to insert attending. And then if I see a 0x01, I insert promptly. And so I iterate over every byte of my shellcode, figure out what the value is, look up that index in my translation table, and insert the word into the translated shellcode array. So this one is what, 267,000 or 265,730 bytes. No magic there. That happens to be a Crowdstrike shellcode. That's all it is. So once we've built our translated shellcode, all we need in our shellcode loader is our translation table, because we need the map. We need the map to map back those values back to their actual shellcode values. And then we need our translated shellcode and this little code stub. So what we're going to do is create a new array. We'll call it shellcode. It's the same size as our shellcode. And then we iterate over our translated shellcode array. And we do this lookup. We have a second index inside. So for every byte, we take that and then we start checking its position in the translation array. So if you remember, back here, if I look at my translated shellcode array and I'm in the first part of the loop and I see that the word attending is there, I know that the value is 0 or 0x00. And so I just continue that process. I'm going through this loop, and if the value is not equal, I just increment the index and check the next word in the translated shellcode array and compare it to my translation table. Or I should say, I compare that value to the next entry in my translated translation table. I really should have used different words for this, so it would be much easier to explain. Really. So, but I think you get the idea, right? Like, I'm iterating now over my translated shellcode. I'm going back to my map, which is my translation table. And if it doesn't match, just go to the next entry in the translation table. And once I find a match, the index of that word is the shellcode value. And I can insert that into my translated or into my shellcode array. And then I can run it. However, that worked for a while, and then some companies started signaturing that routine. And brittle signatures are brittle, so they're really easy to break. You could do things like insert a printf. That's all I did. And then Defender's like, I don't know what this is. It's fine. By simply inserting a printf inside that loop. It doesn't print anything out. It doesn't do anything. You can also do things like opening up the null device and closing it. And that is enough to change the signature as long as you are disabling compiler optimization. And this works. So this works for evasion, and now, every once in a while I have to tweak what that evasion step is, but that's all it takes. And so the results of this, if you remember, the previous one was 15 megs. Well, now English.exe, which is the Jargon version, and why did I not call it Jargon.exe? Don't know. Wanted to make future Mike's life hard. So English.exe is our Jargon encoded shellcode loader. It's 1.7 megs. So it's still bigger, but it's not 15 megs, right? And when we try to compress it, I compress it by 85.8%. So not as good, it's not as low in entropy as compiling in the raw words, but now I have a shellcode loader that contains no shellcode. So it's harder to analyze, and it's low in entropy. So does it get past, in this case, Crowdstrike? Well, let's see. We got a beacon. So it works, and we still use this technique all the time. It's highly effective. It has been incorporated into other tools like Ballast Kit, their macro pack and shellcode pack. They included this technique, and it works most of the time. A few EDRs seem to have caught on to it. Through some troubleshooting, we think that it's actually the dictionary that Ballast Kit is using. It just needs a larger potential word set so that those combination of words don't keep coming up. You just have to change the dictionary, then it bypasses any detection, and that's right. So this still works. Just keep changing your dictionary. As long as you keep using randomly generated arrays, you shouldn't have any signature for this. And of course, everything else still has to be good, right? Like, you can't mess up the other parts of the execution chain, or otherwise you will get detected. So if you want to play with it, it's on our GitHub. I've written a blog about it. That's at redsiege.com/jargon, and it is available for you to use. I encourage you to use it. For the defenders, I'm sorry, I do not know how you detect this other than doing some type of frequency analysis. And if you looked at that gigantic array of words and started doing some frequency analysis, you might be able to come back and go oh, I think this is shellcode. But the thing is, yes, I feel bad because there's really no detection for this, but, and I've been a defender, I've been in your shoes, I still have to do every other part of the chain correctly, and you still have lots of ways of detecting me, so I feel bad, but not too bad. So that's Jargon, and I'm going to talk about Jigsaw in a minute, which is another shellcoding technique, but does anyone have questions on Jargon right now?
You picked English as your base language. Is there a preference, and why not go with other languages, or could you go with other languages for using Jargon?
Yeah, so I used English because I have an English dictionary laying around as part of my shellcode toolkit. We use it for lots of different purposes. So I had that. That's why I made that decision. But if I was operating against, say, a German company, and I wanted to blend in, I would probably use a German dictionary, or I would change that dictionary based on who I'm targeting and the environment that I'm in. For instance, if I wanted to pretend that I am a Cisco WebEx loader, I might go extract the strings out of the Cisco WebEx updater and then use that. As long as it has 256 unique strings, it now looks much closer to the Cisco WebEx updater. So that's a great question. I just use English because that's what I have, but changing it like that would be really good from an OPSEC perspective. So that is a awesome question. Thank you.
Is there any encryption in that loader at all, or is it just encoding the jargon?
No, there is no encryption at all. It's just encoding. All we're doing is looking at a byte and mapping it to a different value. So, I mean, it's a little more complex than a Caesar cipher, but not terribly. But writing it, man, getting my head around it, that was a pain. That was a pain. And I had an off by one error in it for a year and a half because I hadn't tried running 32-bit shellcode. And then I was getting ready for something and I was trying to write 32-bit. Actually, Daniel, I was getting ready for you for the thing that we did together. I'm trying to run 32-bit shellcode. And it's the morning before I'm supposed to be recording a segment on it, and it doesn't work. And I'm sitting in my hotel room just like screaming, like, oh my God, it's not working. It's not working. What is going on? What is going on? This worked before. And then finally, like debugging, like just seeing where things mapped out, I was like, oh yeah, that loop has to be less than, 255, like less than or equal to is a very different comparison operator.
Do you feel like it would be more effective to have the code that you wrote pull in high entropy generation of words to create a low entropy binary for further enhanced evasion? So
if I understand the question, like would I actually choose words like
completely random word selection across any gamut of words and or languages potentially?
That's an interesting question. And like it could definitely be more effective. I'm a utilitarian programmer. I need to, GSD, right? Like, and then I GSD and I move on. Like I got the problem done. I solved that problem that I was thinking about. It works. I'm going to move on to the next thing. Because like this could be way more efficient. Like someone submitted a request for, because the way that I was generating it in Python, it was like painfully slow. It would like take minutes. And someone's like, oh, just do this. And it was instantaneous. And I was like, that's brilliant. I was just like, I can kill 5 minutes whenever I need to do this. And so there's probably way better ways of making this more efficient. And I accept pull requests.
So when you were testing this against EDR initially in the initial concept, what was like the level of entropy that EDR would detect on, or rather like what level of compression did you find? I won't hold you to exact percentages, I'm just looking for an idea.
Yeah, so that is a great question. And once again, we're going into the GSD school of thought. That's getting stuff done. Stuff, exactly. And like I did something and I did something else and that something worked. And so I moved on. And I never actually went to see like what the threshold is. And I intend on doing that for some other tools as part of a blog series that I wrote last year. I'm going to update it, but I haven't gotten to that point yet. So I don't know where the threshold is. And I also think that it's probably not static. I think it depends on like a bunch of different factors. Like I can't imagine that they were just like, oh, if it's above 53%, flag it. But also, man, the amount of stupid things we see. So it's possible.
So are they checking entropy across the entire file, or is it just one section? Because theoretically, otherwise you could just DD to the end of it with all zeros, and now you have a highly compressible file, but it's not actually, like, you're just adding junk to the end of it to make it compressible.
Right. So that is a great question. Are they measuring the entropy across the whole payload or in certain sections like the text section or the R data section or whatever? And again, we GSD here. So it got it working and that's all I need to know. But certain EDRs do look like they're looking at specific sections rather than just the file as a whole. And to your point about appending like zeros. So there are tools out there that do that. And I actually have a tool I wrote called Digdug that will append English words to the end rather than zeros because some EDRs look at that padding. So basically you can just concatenate a bunch of zeros or data onto the end of an executable and make it bigger. And if that data that you're concatenating on the end is low in entropy, you drive the entropy of the whole thing down. And there are some EDRs that look at that appended data, and if it's null bytes or like zeros or highly random data, like they'll alert, but they don't if it's just English words or some kind of words. But once again, I got to where I needed to go and I moved on. So these are all great questions. Like I appreciate them. And I apologize that Mike was in GSD mode and did not do further research. So that's why I'm not really a researcher, because a researcher would ask those questions and like come out with a big graph and be like, here's the magic point. And I'm just like, next. Okay, so I wrote another tool called Jigsaw, and you can get the slides at jigsaw-toolshed@redsiege.com. Hold on with me, please, with this one, because I wrote this tool and I don't understand how it works sometimes when I try to explain it. So, I should have asked that. Hey, it's me. So Jigsaw got its name from a jigsaw puzzle, right? Like, when you have a jigsaw puzzle and you haven't put it together, you just have this big mess of pieces. And without the picture on the front of the box, it's really hard to put it together. You can, but it's very hard. And my wife loves doing jigsaw puzzles, and I was thinking about other ways of obfuscating shellcode, and like I was looking at this jigsaw puzzle, and I was like, I wonder, how would I do this? So the second bullet, someone's probably going to call me on it, and I actually don't know if Jigsaw results in lower or higher entropy, and I'm sorry. I wish I knew the answer to that question, and I told someone I was going to answer it after Deadwood, and I was GSD, and now we're here. So I don't know, but I wanted flexibility. I wanted more than one trick in the deck. Like, I wanted different tools and change my signatures. So I wanted another way of obfuscating shellcode. So Jigsaw, at its most basic, takes shellcode, cuts it up into individual chunks, shuffles those chunks and stores them, and then at runtime reassembles those chunks into the proper shellcode. Is it lower entropy? I hope so. I think it is, but I don't know. Like, when you do encryption, you're actually changing the data, right? Like, you're taking data this, you're encrypting it, it's something completely else. All I'm doing is taking the data and shuffling it around. So I don't think that would significantly increase or decrease entropy. But this is how it works. I write all my tools in Python, so it's in Python. So I use a list because Python can't have arrays because Python. So I have a list, which is an array. I have a list of positions that is equal to the length of my shellcode. So if my shellcode is 100 bytes, I need a list that is 100 bytes long, has 100 entries. And then I'm going to shuffle that list. So if I populate it with a range of 0 to 10, and then I call random.shuffle, and I look at the contents of that, we now see that we have 10 bytes, but they're in a random order. And that's the key to how Jigsaw works, because we're going to now start doing the same kind of lookup thing that we did with Jigsaw. And this is where it gets hairy. So I'm going to create a new empty list called Jigsaw, and Jigsaw is where I'm going to store my shuffled shellcode. In retrospect, calling the key Jigsaw would have been a lot better, but here we are. So I'm going to create a new empty list called Jigsaw, and I'm going to iterate through my positions list, and I'm going to look up shellcode at that index. So, oh man, what the actual? Oh, okay, no. Got to look at your slides and remember what you're doing. So this part might be a little bit confusing, but you'll see how it works. I'm not actually sure it works correctly. I am so sorry. Like, I try to be more on top of things, and I thought I was, but this is what happens when you work on slides late at night. Let's go over here to this deck, because I know this part is right. And you'll understand, like, if you understand how I put the puzzle back together, you'll understand how it was deconstructed. So let's say I have 5 bytes of shellcode, 00, 01, 02, 03, 04, 05. Why is that 6? Why is that 6? Oh my God. Please have someone proof your code. Proof your, like, normally, is there? Okay, good. I thought there was 5. 0, 1, 2, 3, 4, 5. Oh, thank you so much. Thank you guys for being here. Like, I'm so paranoid because I was so confused trying to explain this last time that I've now confused myself preemptively. 0, 1, 2, 3, 4, 5. Zero-based numbering system. That is, in fact, 6 entries. So I have 6 bytes of shellcode that I'm going to populate with zeros. I've got my positions, which is my randomly shuffled list that we generated in Python. So the random order of these bytes is 0, 5, 2, 4, 3, and 1. And then I have my Jigsaw, which is my actually shuffled shellcode. Because that first line you'll notice is commented out. I wouldn't actually, like, that doesn't do anything. It's just helping you understand what the original shellcode was. Now I've got this list, and I create an index called IDX, and I set my position integer equal to the value that is at the positions array at that current index. And then I insert into the shellcode position, that specific value, the byte that is in Jigsaw at that index. And so now I'm going to show you some bits moving around that will hopefully make more sense. So in the first iteration, the first value in the positions array is 0. And it happens to be that the first value in the Jigsaw is 0x00. So when I iterate through this list, my index is 0. So position equals position 0, because remember that's position IDX. So I'm going to grab that value that is at position 0, which happens to be 0. So now I'm going to insert into shellcode 0 the value that is at Jigsaw 0. So now my shellcode array looks like 0x00. It actually hasn't changed because I populated it with all zeros, but that's what went in there. So now I'm on the second iteration. I'm at index 1. The value is 5, which happens to be 0x05. Just happens to be the way this worked out. And position equals positions 1, because now we're at index 1. So shellcode 5, because the value that is at positions 1 is the number 5. So I'm going to insert at shellcode index 5 the value that is at Jigsaw index 1. And then, of course, I didn't update that value because I was copy pasta. Ignored the 0x00. And now we see that the last byte in that list is 0x05. Only works if you point it this way. So now we are on the next iteration of our loop, and we see that the value is 0x02. So I am going to then insert, I'm going to grab the value at positions 2, which happens to be 2. So I'm going to insert at shellcode 2 the value that is at Jigsaw 2, because it happens to work out that way. Because it was even more confusing when I was just using like actual shellcode bytes. Like, you should have seen the mess at Deadwood's Toolshed trying to explain this. The video's out there if you want. It's fun. So that's how it works. You can try it out if you want. And I know it's confusing, and I wish I could explain it to you better. And I've tried explaining it so many times. And it's like, I know it works. I'm not sure I can fully explain to you in a way that is elegant. But it does work. We use this on a regular basis. Have not had any signatures for it at this point that we've had to deal with. So it's another tool in the toolkit that you have when you're trying to have shellcode loaders. And in fact, I wrote, if you look at the third line, Adventures in Shellcode Obfuscation, I wrote a 14-part blog series last year of a bunch of different shellcode obfuscation techniques and then compared how effective they were. And that is out there. There's a blog for each technique. There is a video for each technique. There is also example working code in a GitHub repository that you can find if you go to that blog. So you can actually practice these techniques if you want. And the point is that, like, you want to use different techniques in different environments for OPSEC purposes, right? Like you might try to blend in, and we know that, oh, they've got Sentinel-1, so I can't use this technique. I have to use this technique. Like the gentleman back there asked about, like, what about using different dictionaries based on the context? If you're in Germany, do you want to use a German dictionary? Yeah, that might make a lot of sense with Jargon. So you want to have a lot of tools in your toolkit to give you flexibility. because it's really painful when you're a one-trick pony and the one thing that you have doesn't work. Like, now what do? You scramble. But if you have a suite of options available to you, just try the next one and try the next one. I will tell you, none of these solutions that I've talked about are perfect. I would love to see them improved upon. I take pull requests, so they're in our GitHub repository. I would love to, if you find a bug, tell me about it. If you have an idea for making it better, tell me about it. But right now, that is the last of that, and it's time for questions.
With out-of-the-box configuration, are there any default signatures at least that could be programmed? And so if someone pulls this from GitHub script kiddie style, there's a way at least to have the basic level of defense, even though obviously use it the full level of robustness that we've talked about, it doesn't matter.
That is a great question. And I think that could be accomplished pretty easily. When I generate my random number, when I'm at that random number initialization phase, so way back here where I call random.shuffle, I could generate it with a static thing. The problem is that list is the length of the shellcode. So I don't know how large the shellcode is. So it'd be I'd have to start with an insanely large list and then chop it down to hopefully the size of the shellcode and hope that no one ever goes bigger. And then just have a special option, be like, use this to generate a random one. And I think the same thing would work with Jargon as well. And that way you could give a default signature. The problem with Jargon is I provide the Google top 10,000 dictionary or something like that. But if they choose a different dictionary, it's all out the window. But with Jigsaw, that would be a good way of providing that. And that's actually a really good idea. Thank you.
Do these tools have the same level of success with staged versus stageless payloads?
That is a good question. I am an advocate of never advocate. I am an advocate of knowing how to speak English. I'm an advocate of never staging whenever possible because it's such a tell. I try not to stage. And really, I mean, yeah, you could do it, right? Your stage one it's a tiny amount of shellcode, but it's also at that point that stage one is such a tiny amount of shellcode that entropy measurements probably isn't an issue, but I don't know because I suspect that it might be the size of it might be the amount of entropy or encrypted data versus the whole size of the executable for some EDRs, and I haven't measured it. So again, I don't know. It was we got this done and moved on. But that would be a good test, and I'd be interested in seeing the results, but it's not something I've tested.
Have you looked into using this technique for other use cases besides shellcode? So for example, if you're wanting to obfuscate maybe sensitive data before you send it out of an environment to get around of what's the term for it? Basically, sensitive data detection tools.
So getting around DLP?
Yeah, DLP, that's right.
No, I have not. I have not considered that aspect. And I think it's doable, but there's a bit of a precursor problem. In shellcode, I know there's 256 possible values, and that's it. If I'm exfiltrating data, and let's say I'm exfiltrating a Word document, I don't know how many possible different words are in there. So my tool would have to do some kind of analysis to figure out, I'll use the word tokens, how many unique tokens are there that I need to represent, and then adjust on the fly. I think it's something possible, but it's not a problem I've tried to solve.
Have you thought about merging Jargon and Jigsaw?
Thanks for the question. No, again, getting stuff done mode, and then it's back to production. There's a lot of cool things that could be done further on these, but once I have something working, it's usually these things come about in the middle of a test. I need to get this working right now. And then I get it working and I document it and I write up a blog for JCon to make JCon happy. And then and then I move on. And that's the last time I look at that unless there's a bug report. So that's how to get a hold of me. I'm on LinkedIn. Follow Red Siege. We have a really good Discord. We are one of the official places to come get information about Cobalt Strike. So with that, I want to thank all of you for being here. This was awesome, and I hope you have a great rest of your conference.